For section 4.1, we're just going to analyze some of the basics of polynomial functions, some details with the graphs, the end behavior, what the functions could look like, and what their power is, and certain signs can influence the shape and direction of the graphs. There's a lot of maybe new vocab words here, so take a chance to pause, look through these. We're just dealing with power functions, so we'll revisit this, where a x to the n power n is some non-zero real numbers here. Leading coefficient is just going to be that ava, the number that's in front attached to your variable. Degree is just going to be the highest power of the function. Monomial just means one, so one term. We're going to look at one term, but then we'll also look at polynomials, which is multiple terms. And end behavior, we've seen a little bit before. We're going to revisit, like basically, just by looking at the function, we can analyze like what the behavior we would expect to see. Okay. And speaking of end behavior, here's what we get into. So depending on the power, so we're looking at our degree, the highest power, if that degree is even versus odd. Okay. If it's even, then both ends go in the same direction. So notice this is even, goes in the same direction. This is another option for even. They both go in the same direction. If our leading coefficient is positive, like an x squared, or they're showing you like 1/4, x to the fourth, it's even and positive, then both ends open up. So as x goes to negative infinity, our y goes to infinity, and as x goes to infinity, y again goes to infinity. Both ends are going up. Left side goes up and right side goes up. That's what I mean, where the ends going. If we just do even, but we make it negative, now we have like a negative x squared, and we've seen those before. It opens downwards. Now everything goes down, so the left side goes down to negative infinity, the right side goes down to negative infinity, so y approaches negative infinity as x approaches left or right. Okay. Notice for our even functions, our domain is all real numbers. Actually, it's all real numbers for every type, but for range, in this case, it kind of hits like a lowest point. It'll be like everything bigger than zero. For here, it's everything less than zero. Okay. If you compare that to odds, we get odd degrees. So, and actually, y equals x to the first, your linear stuff that you did is an odd degree, and you would have just a line going up in one direction, down in the other direction. As we add higher powers, like x to the fifth, x to the third, what we see is like one end goes down, one end goes up. So every odd function will have a behavior like this. If it's positive, it goes this direction. So kind of like a linear thing goes like it's increasing basically the whole time. If you just make it negative, like a negative x cubed, it'll flip it and go in reverse. So it's like decreasing the whole time. So nothing too bad. Notice here, domain and range is all real numbers because it goes down forever and up forever. So we use everything. So it's actually kind of good to be odd. You don't have to worry about any sort of domain or range restrictions. We will talk about the zeros here more. Zeros are really just your x-intercepts. So notice like when you have an odd function, you have to have at least one real zero. There's no way it can go down and forever and up forever without crossing the x-axis. But you could have a x squared or something like that like, for example, is up here and won't hit the x-axis. So it's possible that there wouldn't be a real zero or an x-intercept. But more about that later throughout the chapter. Okay, so let's just look at this function. Of course, you go to Desmos or any graphing thing and graph it and see what the actual thing looks like. But some of these actually get quite large and difficult to see the full picture. That's why it's good to know something about the behavior. I know this one here. Okay, so it's odd with a negative leading coefficient. Oops, sorry, did we do that? So odd and a negative leading coefficient, I just abbreviated LC's leading coefficient, should have a shape like this, like we just saw on the previous page. So it's going down this way here. So up as we go to the left and down as we go to the right. So it has that behavior. In other words, as we write it out, as x goes to negative infinity, as I go to the left, negative infinity, y goes up to infinity. On the other side, as x goes to the right, or as x gets more positive, x goes to infinity, then y is going down to negative infinity. And they could use y, they might use f of x, same idea. As far as domain and range, they'd be the same, negative infinity to infinity, because it keeps going up and it keeps going down. See, we can tell a lot just by looking at the power without even having to go to the graph. Here now we have an even degree and a positive leading coefficient. So even and positive would be both ends going up, kind of like your typical parabola. In this case, our end behavior is both ends go up. So as x gets more negative, our y value goes up. As x gets more positive, our y still goes up. Both ends go to infinity. Domain is everything, negative infinity to infinity are all real numbers, but our range is going to be 0 to infinity. It keeps going up, but it will like hit this lowest point and go back up. And you can even graph it and see that it passes through 0, 0. All right, we could also look at like some word problems here. We got this like power function they're talking about here that has to deal with flow of a garden hose and all that stuff. So feel free to pause and read through it. Basically, we can see our function is defined by p of f equals 3 over 2 f squared. Graph this function and state the domain and range. Well, we can learn a lot just by looking at this. It is our leading coefficient of 3 over 2, our a value, if we think about the a value is our leading coefficient, is 3 over 2, and the power is 2. Our domain, therefore, would have to be negative infinity to infinity, and our range would be everything bigger than 0 because a is positive and n is even. So we got it even and positive like we just saw. So both ends are going to go up forever. Domain is negative infinity to infinity for everything that we're seeing so far, unless we come across a restriction with a real world problem. And here be everything greater than or equal to 0. They're even plugging in some different numbers here just to get the y values. I mean, you could use Desmos for this. If you just go to Desmos, type this in. I mean, I would use like x and y maybe instead. But you can get a table and plug in your own numbers and check it out and fill in these numbers here. Otherwise, you're just taking like, for example, -2, plug it in for f, squaring it, times it by 3 over 2. That's what they're doing here to get an answer. Okay, and then you get a graph that looks like this. So there's no real trick to graphing these. You just have to get enough points. So if I plug in enough x values, I'll get enough y values to plot these points. See, it goes through -2, 6. It goes through -1, 1.5, 0, 0, and so on. All right, some more vocab. Now we're just talking about a full polynomial, which will be something like these guys here. This is a full polynomial, lots of terms. It really just boils down to like the most important thing is going to be that highest degree. So degree is going to be the highest power, and that leading coefficient. Those still dictate the shape. Standard form means we want to arrange them in descending order, so highest power first, then down from there. Polynomial in one variable is what we're talking about. All this here stuff, axn, all that stuff. Basically, n is a non-negative integer. N is different powers, as you can see in some of these examples here. Like here we got x to the fourth, x to the third, x squared, x to the first, or just x, and then a constant there. So those are polynomials. Quartic and quintic are just some other names you could give to a fourth degree. Like we have, x squares are quadratics, x to the third is a cubic, x to the fourth would be called a quartic. Think about 4 quarts, and quintic would be x to the 5th power. Not that you have to know those names, but you might just see them pop up here and there. All right, so say the degree, leading coefficient, and if it is a polynomial in one variable, and use it to determine the end behavior. So this one here is definitely a polynomial. I'm looking for the highest power, which in this case is x to the 4th. So it's even and it's positive, so it opens both ends up. So we've seen that before. Both the y values are going to be approaching infinity to the left and to the right. Here's 7x cubed. That's what I'm going to be focusing on. That is odd, and the 7 is positive, so it should be some sort of shape like this. So as x goes negative, our y goes negative. As I go to the left, I'm going down. As x gets positive, as I move to the right, then y is going up. This one is not a polynomial in one variable. We can see we have y and x all attached together, and that's not what we're talking about here. That's not a polynomial that we're going to explore and study. This one here is okay, but just be careful. They tried to trick us. The highest power is actually way over here. They did not put it in standard form. So really it is an odd degree and it's negative in front of it. So it should be a shape like this. In other words, as x goes to negative infinity, y goes to infinity. I need to space this out a little better. Sorry guys, if that looks a little confusing there. Let me space that out a little better for us. Those go together. Basically, as you move to the left, the y value goes to infinity. As you move to the right, as you move to x is infinity, y goes down. This one here, the 6 over x is really x to the negative first power is how this could be rewritten. We cannot have negative powers, so therefore this is not a polynomial in one variable. We're only looking at things like these guys here. All right, a few more examples. Maybe a few more word problems, so feel free to pause and read through it. The basic idea here is this really crazy long polynomial, but we could use it to find answers and graph it and figure out what's going on. We're doing a radius of 60%, so I need to change it to a decimal, percent as a decimal. So it's 0.6, and I'm just basically plugging that in for all of the x's. So I'm just gonna go here and plug in all those x's. Definitely would probably wanna use a calculator here or Desmos. You could type all of that in at once. Just watch your decimal places, watch your powers that you're typing in there. You should end up with 0.6224, in this case, grams per cubic centimeter. Grams per cubic centimeter. As far as graphing it, well, there's no trick to this. You just have to get points. My recommendation is definitely use Desmos, type this in, get your table, and I'll show you how to do this in class if you're not sure, and you can actually edit the table to put in whatever x's you want. They definitely want to look at decimals here because we're only looking between 0 and 1. That's what they told us. Between 0, like basically 0% and 100%. And that way I get these numbers here and I can easily get those from the table and then plot it and you get a picture like this. I'll even show you in class how to change your windows so you can see what they see and how they see it, instead of like maybe a more awkward graph that has numbers that we don't really need to see. All right, zeros, also known as roots, also known as your x-intercepts. So we're going to be exploring in this chapter and the one beyond, like how to find the zeros. In this case, we're just trying to state the number of real zeros. So the real zeros are just where do I hit the x-intercepts? So it looks like I have 3 real zeros in this one because I have 3 x-intercepts. This one has 1, 2, 3, 4. More about this down the road as we want to like solve these. If you come across something in practice, they don't give you the graph, you can graph it yourself and then count the number of x-intercepts. All right, our last one is we're just going to compare some functions. So g of x is already graphed for us. That was very nice of them. F of x is given as an equation here. What I'd recommend is you just graph both. So that's what they did here. They went to the table, they plugged in some values of x to get the y values, and they plotted the points. You could just go to Desmos and graph f of x here. So we've got g of x over here and fx over here. Feel free to use your Desmos and get a table that way. So who has the better relative maximum? So we've talked about maximums before. This guy has a maximum right here. This guy's got a maximum over here. We can see on f of x, it's a little bit higher. It's at 6 versus like somewhere between 2 and 3. So fx has the greater relative maximum. We see relative maximum because there are points that are still higher on both of these graphs. So neither one has a like true maximum, like an absolute maximum. Otherwise, you're just comparing other things like finding, the zeros. Well, where are your x-intercepts? So -3, 0, and 1 for the f of x, and then -1, -0.5, 1, and 2 for g of x. Which actually, your zeros are the same as your x-intercepts, so notice how these duplicate over here. They also found the y-intercept on fx at 0, the y-intercept over here on g of x is 2. And then just the behavior. Notice they do have different end behavior. Fx, as x gets more negative, it goes down to negative infinity. As x gets bigger, it goes to positive infinity. And then g of x, both ends are going to positive infinity.